Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 9th, 2025. We're discussing a paper from the International Conference on Learning Representations, or ICLR, called Data Scaling Laws in Imitation Learning for Robotic Manipulation, published a little over 3.5 months ago on January 22nd, 2025. This paper investigates data scaling laws. These are principles about how performance changes with more data for robots learning through imitation. That's where robots learn by watching humans. The goal is to see if they can achieve zero-shot generalization, meaning perform tasks well in new environments or with unseen objects. Okay, so to explore these data scaling laws, the researchers used several real-world robot tasks. This first figure shows 4 examples: pour water, mouse arrangement, fold towels, and unplug charger. They primarily used the first 2 tasks to derive the scaling principles, and then validated these principles on the other 2. The robots' learned strategies, or policies, were trained using diffusion policy. Diffusion policy is an AI model that learns how to generate robot actions from demonstrations. For vision, they used a DINOV2 visual encoder. A visual encoder processes camera images so the robot can see, and DINOV2 is a specific, powerful type of this encoder. Okay, building on those tasks, these next 2 graphs illustrate environment generalization, which is the robot's ability to perform well in new, unseen settings. We're looking at the pour water and mouse arrangement tasks again. The vertical axis shows a normalized score. That's a performance rating from 0 to 1, while the horizontal axis shows the number of different training environments. Performance generally improves with more environments, following an approximate power law relationship. A power law relationship means that performance increases steadily as you add more, though the improvement might get smaller with each addition. Crucially, the diversity of these environments often matters more than just piling on more demonstrations within the same few. Alright, so after looking at how robots adapt to new environments, these next graphs shift focus to object generalization. That's how well the robot performs with objects it hasn't seen before. Again, for pour water and mouse arrangement, we see the normalized score on the vertical axis, but this time, the horizontal axis shows the number of different training objects. The different colored lines represent using different amounts of the total demonstration data. And just like with environments, performance generally climbs as the number of distinct objects increases, following a similar power law pattern. This really highlights that variety in objects is also super important. So building on that idea of performance climbing with variety, these next plots really visualize the power law relationship we've been discussing. We see 6 graphs here for the pour water and mouse arrangement tasks. The vertical axis shows the optimality gap, which is essentially how far the robot's performance is from a perfect score, so a smaller gap is better. Both axes are on a logarithmic scale, which means a straight line indicates a power law. And indeed, as the number of training objects, environments, or unique environment object pairs on the horizontal axis increases, this optimality gap consistently shrinks, following those straight dashed lines. Okay, so those previous plots showed the optimality gap shrinking nicely. Now, these next 2 graphs, again for pour water and mouse arrangement, directly plot that normalized score on the vertical axis. The horizontal axis shows the number of unique training environment object pairs. Each colored line here corresponds to a different fraction of the total demonstrations used for training. We clearly see that as you increase the number of these diverse pairs, the robot's performance consistently improves. This really underscores the idea that having many unique combinations of environments and objects is crucial for generalization. Alright, so we've seen that more unique environment object pairs boost performance. These next 2 heat maps, for pour water and mouse arrangement, dig deeper into data diversity for imitation learning. Imitation learning is teaching robots by demonstration, like showing someone a task. The horizontal axis shows different environments, the vertical objects per environment. Brighter colors mean a better normalized score. This really highlights that increasing environment diversity is key for strong zero-shot generalization. That's the robot succeeding in totally new situations it hasn't been explicitly trained for, showing the importance of varied training. So, looking at all these results, from the performance curves to those heat maps, It's clear this research offers some really practical insights. The big takeaway is that for robots learning by watching us, what we call imitation learning, variety is truly the spice of life. Focusing on diverse environments and objects, rather than just tons of repeat demonstrations, is far more effective for teaching robots to handle new situations. This means we can achieve impressive generalization with a smart, efficient approach to collecting data. That's all for this AI Research Roundup. Thanks for tuning in, and I'm your host, Alex.